Hello everyone, my name is Pracheta Amarnath and I will be presenting our work on estimating the prevalence of multiple chronic diseases via maximum entropy. This is a joint work along with Ninad Khargonkar, Prasanna Srinivasan, Roshan Taikat, Hari Balasubramaniam and Peter Haas. Chronic diseases are defined as diseases that last a year or more, require ongoing medical attention and/or limit the activities of daily living. In the US, they are responsible for 70% of deaths and cost the economy roughly $3.7 trillion annually. In reality, multiple chronic conditions, or MCCs as I will refer to them henceforth, play a bigger role in our healthcare expenditure. MCCs, which are the presence of two or more chronic conditions in an individual, have a disproportionate impact on the costs associated with chronic diseases. Why is this the case? When patients present with MCCs, greater coordination is required amongst the different specialties due to fragmentation in care, which leads to higher overall costs. There is a strong need to estimate the MCC prevalence. Why? We can seek to improve the population health by improving epidemiological understanding of MCCs and provide inputs for intervention policies for public health. We can also develop resource demand models for personnel, equipment, and facilities planning. So, what is the biggest challenge in estimating MCC prevalence? Real-world datasets are limited and extremely sparse. Note that we denote the number of diseases by K and the number of patients or rows by N. The dataset that we have and use in our research has 62,000 rows and roughly 230 diseases. However, what we need to estimate is the probability of 2 to the power K disease combinations. Even if we take K as 20 for the top 20 most prevalent diseases, that turns out to be over 1 million probabilities. To summarize, our key challenges are: large, dense data is not available because such data is expensive to collect. Most of the disease combinations whose probability we want to estimate are not seen in the limited, sparse data that we have. It is highly likely that the true probability of many of these disease combinations are not zero, and our initial experiments with real-world data indicate that these overlooked disease combinations can potentially have significant impacts on healthcare. In light of these limitations, maximum entropy is a principled way to solve this problem. But what does maximum entropy mean? The principle of maximum entropy is that we use the simplest distribution that is consistent with the given information. That is, we account for all the information we know about the diseases and assign the probabilities accordingly. It is worth noting that maximum entropy is a pay-as-you-go approach. The more information it has, the smoother is the approximation to the real data at hand. For a vector R in the set of all possible disease combinations, the entropy is defined as the sum over all vectors, the probability of the vector into its log probability. We can describe this principle with the help of an example. In our first dataset A, we wish to estimate the prevalence of 3 diseases: high blood pressure, denoted by HBP, diabetes denoted by DB, and heart disease denoted by HRT. We have no other information that is available to us. In the absence of any information, you are not likely to get one combination any more than the other. So, MaxEnt, short for maximum entropy, keeps disease occurrence as uniform and independent as possible. It assigns equal probabilities to the 2 to the 3 combinations available here, and that probability is 0.125. What happens when we do have some more information about the diseases? Let us see how maximum entropy would work. In example B, we have been told that the probability of HBP is 0.7. We can represent this constraint as the marginal probability of HBP, which is obtained by calculating the probability of HBP given all combinations of the other 2 diseases. Similarly, we are told that the probability of dB is 0.3. When we maximize entropy subject to these constraints, we obtain the probabilities as shown in the table here. We can verify that by summing up the marginal probabilities of HPP, that is the last 4 rows, and dB, that is the rows where diabetes is equal to 1, we satisfy our constraints and maximize the entropy. Note that the probability of HRT is uniform as there are no constraints for HRT. Also note that the probability of HPP and dB together is the probability of HPP times the probability of dB. In our final example C, we demonstrate the form of constraints that we are using in our approach. We have the marginal probabilities of HPP and dB, which is 0.7 and 0.3 respectively. But we also know that the probability of HPP and dB occurring together is 0.1. After maximizing entropy and obtaining the probabilities, we can verify that these constraints are satisfied. Note that the joint probability of 0.1 for HPP and dB means that the two diseases are less likely to co-occur than under independence, since the product of their marginal probabilities is 0.21. So, what constraints do we want to include in our dataset? Ideally, we want to include constraints that we trust, that is, constraints that have a strong support in the data that we have. As you saw in the previous example, constraints are of the form P of S is equal to support of S, where S is a subset of diseases and the support is defined as the number of patients with at least the diseases in S divided by the total number of patients. This leads us to two key questions. How do we efficiently find the set of diseases from the data that we have, and what should be the minimum support that we should use to determine the set S? To find the constraints, we use a frequent item set mining algorithm called FP growth, and to find the support, we learn it from the data using machine learning techniques. I will explain both of these points in greater detail now. FP growth algorithm is a frequent item set mining algorithm. It's also known as market basket analysis that can quickly go through all 2, 3, 4, etc. disease combinations that appear with a larger frequency than we have mentioned in the dataset. The result of this algorithm is these combinations as you see in the diagram. For example, hypertension, lipid metabolism disorders, and diabetes are constraints that we can use in the maximum entropy model. However, the FP growth algorithm requires that we specify what the minimum support is. How do we find that minimum support? Ideally, a clinician or expert could provide the support that corresponds to the most important combinations that are prevalent or required to be analyzed. But in the absence of such information, we can learn the correct level of support from the data. How do we do this? We can generate lots of diverse synthetic datasets that plausibly resemble the real datasets, run maximum entropy for a range of minimum supports, and find the minimum support that gives us the best fitting distribution. Then we use this data to build a predictive model for the optimal min support value for the actual datasets. In real data, the number of people having varying number of diseases tends to follow an exponential curve. So our synthetic data generation model reproduces this behavior. We fit generation parameters to match the actual dataset and then systematically perturb these diverse but plausible synthetic datasets. These exponential parameters, along with the number of patients and diseases, comprise the dataset features that we will use for machine learning. We create training data comprising pairs of dataset features and corresponding optimal min support values, one pair for each synthetic dataset. We found that a simple polynomial regression approach produced the best predictive model for choosing the min support. Putting it all together, given sparse real-world data, we run the machine learning algorithm to learn the model for predicting the minimum support. Running FP growth algorithm with this minimum support generates constraints for our model. Running maximum entropy using these constraints then generates the probabilities of every disease combination. We will now show the results of maximum entropy applied to real data. The data that we consider is from MEPS, which stands for Medical Expenditure Panel Survey, which is a nationally representative sample containing disease prevalence and medical costs associated with number of diseases. We use the data from the years 2010 to 2014, which contains approximately 62,000 patients. While MEPS collects data for 230 diseases, we choose the top 20 most prevalent chronic diseases for our analysis. This figure plots the number of people having no diseases, number of people having 1, 2, 3 diseases, and so on. The blue curve plots the results for the prevalence shown in MEPS data, that is, the empirical distribution, while the orange curve is the estimated prevalence as obtained by running our algorithm. While the two lines look really close, we will see in the following slides that there are indeed some significant differences. In our estimation procedure, we first calculate the costs for a number of diseases according to the estimated prevalence given by the MaxEnt model. We looked at costs for people up to 8 diseases and fitted a line. The addition of a single chronic condition increases the mean cost by roughly $2,100 for every person every year. We think that this is a rather conservative extrapolation because the coordination costs actually rise sharply. The differences between the empirical and the estimated prevalence leads us to the following key conclusions. We find that people with 12 or more diseases in the US population do not appear in the empirical distribution at all, whereas MaxEnt estimates 6,740 such individuals for whom the estimated mean medical costs are $177 million, with the possibility of it being much higher. We should perhaps target this population for interventions. The MaxEnt solution also revealed many disease combinations that are unseen in the MEPS data. A few of these disease combinations and their estimated prevalence in the US population is listed here. This information could be used to predict epidemiological trends for MCCs or develop interventions that are tailored to these combinations. In conclusion, since MCCs have a disproportionate impact on the healthcare system and data available is limited and sparse, it is important for us to estimate them. We have come up with a novel, principled approach to prevalence estimation, which involves maximum entropy, item set mining, and machine learning. We also have shown how the impact of medical costs of MCCs greater than 12 is significant, and how our algorithm can also predict disease combinations that are unseen in the dataset. These results can potentially help in combating the negative human and economic impacts of chronic diseases. Thank you.